Good morning. This is page 95 of the note spiral, and we'll be talking about the normal curve, and this will be a brief introduction to the normal curve, and then we're going to spend a lot of time over the next several videos developing ideas about the normal curve. I will say this, the normal curve is an incredibly important concept. We will revisit again when we talk about probability, and actually it's one of the most powerful ideas in statistics because later in probability, we'll learn something very simple concept known as the central limit theorem. And what's great about that is if it says if we have a large enough sample, then everything becomes approximates the normal curve. So consequently, this is an incredibly important idea that applies to large populations. The normal curve is bell-shaped and symmetric, which means the mean, the median, and the mode are all the same. And it's based on the standard deviation of it. I have three normal curves that happen to have the same mean, but different standard deviations drawn below. Before I show them to you, I need to let you know that they don't necessarily have to have the same mean. They don't have to have the same standard deviation. These do for comparison purposes, but you can have all sorts of different means or centers. So they can be centered at different locations, and we'll see that in the subsequent video. So first off, in this case, the mean is located at the center of the graph, so they all have the same mean. But we notice that they're spread out differently. So we see a spread out of 0.5 for this really tall one, a standard deviation of 1 for the middle one, and then one that's more spread out has a standard deviation of 2. Please note, every single one of those graphs have the same area. The area under the curve is always 1. All right, the area under the curve is always 1. So as you increase or as you decrease the standard deviation, it's like you pressed a water balloon and you pressed it together and it grew tall. All right, pressing it together and it pushed up. If you increase the standard deviation, it stretches out, but the area still remains the same. So the water balloon will become flatter if you have a large standard deviation. Okay, they have this awful, horrible looking formula that I believe in calculus BC you get to integrate, but not something we fool with. You don't have to worry about it. You don't have to memorize it, but people go, hey, what does it look like? Well, that's the formula for the normal curve. Please note, normal curve refers to a family of curves. There's an infinite number of them, but they all have that basic formula. What determines what the normal curve looks like is where the mean is, what the mean is, or where the center is, and what the standard deviation is. All right, the mean and the standard deviation determine that. Why is it powerful? We can use it to describe many things in a world that, and I mean, naturally, many things follow the normal curve. Your SAT scores do, so do your ACT scores. A lot of characteristics of nature, such as height, weight, etc., follow the normal curve. That said, things that don't even follow the normal curve, like income in the United States doesn't follow a normal curve. However, if we talk about we take a large enough sample by a concept that we'll discuss much later, the averages will become normal by central limit theorem, or approximate the normal by central limit theorem. So the normal curve is extraordinarily important. I will say this, anytime you're doing work with a normal curve, you need to draw a picture and label it. It's not so much that I'm going to grade it, but I guarantee your scores will increase substantially. One last thing, theoretically, almost all the data lies within 3 standard deviations of the mean, and we'll talk about that in just a moment. When I say almost all of it, 99.7% falls within plus or minus 3% of the plus or minus 3 standard deviations. So that's almost a full 50% within um, on each side. So 99.7% lie within plus or minus 3 standard deviations. Once again, the normal curve, extremely powerful, and that's our introduction.